Okay, welcome to the second lecture in this series of calculus videos. Today what I want to talk about is more simple function related stuff. In particular, I want to talk about some of the most simple functions, which are lines, and then the concept of continuity. So first thing, talk about lines, or their fancier name, linear functions. So if I say a function is linear, I just mean its graph is a line. So linear functions, there's a few sort of basic notions that we need to be familiar with a line. So definition, first of all, definitions, plural. So if, I don't know. Yeah, if f of x is a line, and maybe we'll say y equals f of x just so I don't have to write the full notation of f of x each time. All this means is that y is a function which depends on x. So if f of x is a line, the slope of the line is defined to be, well, what is it defined to be? It's defined to be, typically we denote it with a little m. This is just an arbitrary choice of a letter, but it's standard notation. So m is going to be the change in y, which we'll typically denote by a delta y, over a change in x, delta x. Okay? And what does this actually mean? Well, it means that if I take any 2 points, then the difference in their y-coordinates, all we do is divide this by their difference in the x-coordinates. And then this is, I might notate this by y1, y2, or x2 minus x1. I said that backwards for y. Anyways, all this means is that m is the change in the height divided by the change in the length that you go. So another way that you might remember this is rise over run. So it is how much we go up per every unit that we move to the right one. So maybe that's another way to think about this. So slope is the number of units we move vertically, either up or down, up if it's positive, down if we're negative, for every 1 unit we move horizontally. So if I told you that the position of a car is linear, then the slope would represent its speed, and it would be for every unit of time we move some distance. So let's actually write that out. So if, maybe example in purple, example, if f of x equals 5x, just 5x represents a car's position in feet. I guess we'll say this is an appropriate unit. Maybe it's traveling very slowly. Represents a car's feet, position in feet at x seconds. Then the car moves at a speed of 5 feet per second. That is, the slope of f of x, or the slope of the line, is 5. Okay? And the idea here, key idea, red. Key idea, slope represents a rate of change. And we'll put a star next to that. Very important idea. So slope here represents a rate of change. If I tell you that a car is moving with this sort of position function, then the slope of this line is telling me about the speed of that car, or the rate of change of the position of the car. Okay? So there's one other, perhaps less important part of a line. So another definition. The y-intercept of a line is just the point, or is just the value f of 0. So basically it is telling you the initial position. So that is y-intercept is the initial value. Okay, so if at the beginning of your problem, typically, if your independent variable is time, then at f of 0 at the beginning of your problem, so at time equals t equals 0, maybe f is representing a position. This is representing the initial position, this f of 0. Okay, so that's just what a y-intercept means. And graphically, it is literally where the line intersects the y-axis. So if I were to draw a graph right here, and I drew a line like so, maybe this is 1, this is 2, then this is the y-intercept. And I'm going to abbreviate this with just int, because I don't want to write the word intercept every time. So we call it the y-intercept because graphically it is where the line intersects the y-axis. Okay, so those are the two main features of a line, namely its slope and where it intersects the y-axis. These uniquely define a line, as we'll see here in a moment. And then also that this key idea, slope represents the rate of change. Very important to remember this. If I ever write something in red, very important to remember that idea. Okay. So the next thing that I want to say is that a line can be written in two different forms. So forms of the equation of a line. So there are two forms of the that we might write a line in. So the first of these is going to be slope-intercept. So if f of x is a line with slope m and y-intercept b, then y, which is f of x, force of habit to write y, this is equal to m times x plus b. And so what is this saying? It's that, well, the slope, we've already shown that m, the coefficient of x, always represents the slope in a line, and then if x is equal to 0, well, then this term is 0, and we're just intersecting the y-axis at the point B. Okay, so this is the slope-intercept form of a line, perhaps the most simplest form. The second form is the form that we will use more often, and the one that will be most important to us is the point-slope formula, the point-slope form. So if f of x is a line, again with slope m, and passes through the point x0, y0. So these are not variables. This is some particular point in the or in the coordinate axis. So if f of x is a line with slope m and passes through this point, then and the form that I'll write this in is y minus y0 is equal to m times x minus x0. Or another way that I might write this, if I just add the y naught over to the other side, I have y, which is f of x. This is equal to m x minus x naught plus y naught. And notice that if I expand this, if I distribute this slope to each of the two numbers right here, and I just do the algebraic manipulation, then I can put the point slope form of a line into a slope intercept form. You could also go in reverse. It's a little bit more complicated to go in reverse, but if you needed to, you could take this and put it into this form. In this course, we're actually going to more or less keep lines always in this form because as we'll see later, this actually gives us more information about a function than does this form up here. Okay, so point slope form, and I'll put a star next to this one. This is the one we're going to use most often. That's an upside down star, and because I can't draw a star straight. But anyways, so these are the two forms of a line. Definitely important to remember them. The second one is the one that we will use very often in this course. So maybe let's do a quick example. So if f of x is a line with slope 2, passing through the point, I don't know, 1, 3, then, well, let's just use our point slope form up here. We have a slope and a point, so f of x is going to equal the slope, m, times x minus the x-coordinate of my point, which is 1, and then plus the y-coordinate of my point. Okay, just like that. So if I give you a point and I give you a slope, then computing the line which passes through that point with that slope is a fairly straightforward manner. You just use this formula right here. And since it's so important, let's go ahead and actually box it in red, because it's important to know that formula. Okay, so that's everything I wanted to say about lines. We will make heavy use of this formula throughout this course, and one might argue that calculus in a large part asks, at least on a very small scale, how much does a function appear to be linear? Okay. Also, there's a funny little joke. So if you've ever played the drinking game Buzzed, they have this card in there, and given these two definitions that we have, I'll let you think about why this card is poorly written. Okay.